In classical electrodynamics, till now we have studied the field equations, that is Maxwell's field equations and conservation laws. Along with these conservation laws, we have also studied propagation of plane electromagnetic wave in different media. Now we are going to start a new topic in classical electrodynamics. This is also a very important topic. Actually, in this topic, we will discuss the interaction of electromagnetic wave with matters. In this first lecture on this topic, interaction of electromagnetic wave with matters, actually we will see just an introduction, that is a preamble of this chapter. What we will study in this chapter, I am just going to introduce it. And in fact, after this introductory lecture, we will actually study the actual topic which we have to study in this regard. You know, when an electromagnetic wave is incident on a surface of a material medium or passes through a medium, then you know there is an interaction between the electromagnetic wave and the medium. Actually, this interaction is properly explained by quantum theory. In fact, when we will study the advanced quantum mechanics, you will see this chapter, that is interaction of electromagnetic wave with matters. But before the advent of quantum theory, a variety of interesting events and effects had been described in terms of classical theory too. So in fact, in this chapter, our aim is to discuss the classical theory, or you can say the wave theory, to explain such varieties of events and effects when an electromagnetic wave passes through a medium or interacted with matters. Actually, this classical theory of interaction of electromagnetic wave with matters is studied on two scales. And what are those two scales? In fact, those two scales are, number one is macroscopic scale and number two is microscopic scale. Now, first of all, we will see something regarding the study on macroscopic scale of interaction of electromagnetic wave with matters. You know that when you say macroscopic scale, it means this is just a bulk scale. We don't talk about anything in terms of particle or atoms or molecules or nuclei, but always we take the system as a whole in this macroscopic description. So when we deal with interaction of electromagnetic wave with matter on macroscopic scale, as I have told you, we don't talk about the interaction on particle level, or you can say atomic or molecular level, or you can say electron level or nucleus level. Actually, we consider the material medium as a whole, and in this interaction, electromagnetic wave with matter on macroscopic level, actually we shall discuss behavior, particularly you can say optical behavior of the plane electromagnetic wave at the boundaries between various media. In fact, the important facts which actually we discuss under this heading, that is interaction of electromagnetic wave with matter on macroscopic scale, the important facts which we will be encountered or which we will actually study are in fact reflection and refraction of electromagnetic wave. Next, we will study Fresnel formulae. Actually, this Fresnel formula is also called dynamic properties of the medium. And after that we will see a very important law which is called Brewster's law. And in while studying the Brewster's law, we will actually discuss the polarization state of the electromagnetic wave. This is a very important problem to deal with the polarization of electromagnetic wave for you. And after that we will see a very important phenomena in detail, that is called total internal reflection and critical angle. The most important fact which we will study in this study of macroscopic scale of interaction of electromagnetic wave with matter is actually metallic reflection. In fact, here we must should note that the reflection of the electromagnetic wave by metallic boundaries form a practical aspect of the subject which is called in fact waveguides. And you will see in fact these waveguides have so many practical applications. So the metallic reflection is just the basic theory which will be used in the study of waveguides. Actually, these waveguides we will discuss at the end of this chapter. So this chapter of interaction of electromagnetic wave with matter on macroscopic scale will be ended after the study of waveguides, and you will particularly study in accordance with your syllabus a rectangular waveguide, and that will be a very important concept for you. Now we will see some thing regarding the study of interaction of electromagnetic wave with matters on microscopic scale. You know, when we say microscopic, it means this study will be in fact on the level of particles, that is on the level of atoms, molecules, nuclei, and elementary particles like electrons. Actually, when a beam of electromagnetic radiation is propagated in a material medium, then you know the velocity of the electromagnetic wave in this medium is actually less than the velocity of this wave in free space. You can see here the velocity of electromagnetic wave in a medium V is given as c over n. You know, c is actually the velocity of this electromagnetic wave in free space, and n is the refractive index of the medium. And you know this n is equal to what? This is actually a square root of mu r into epsilon r. You know mu r is relative permeability of the medium, and epsilon r is dielectric constant of the medium or relative permittivity of the medium. I have also discussed that this mu r is equal to 1 when the medium is non-magnetic. But in general, this n refractive index is a square root of mu r into epsilon r. And as you know, this refractive index n, or the square root of mu r into epsilon r, is always greater than 1. And if the number in denominator is greater than 1, what does it mean? It means this velocity v of the electromagnetic wave in a material medium is definitely less than c, which is its speed in free space. So you can say that velocity of electromagnetic wave in a medium is always less than velocity of this wave in free space. Again, one thing is very remarkable here, that in the same medium, if the electromagnetic wave of different wavelength travels, then it is found that the velocity of different wavelengths is different in the same medium. So you can say that velocity v of the electromagnetic wave is actually a function of wavelength, or you can also say a function of, let us say this is a function of wavelength. Now you can see from here that this V is actually equal to C over N, and C is an absolute constant. So you can say if V is a function of lambda, what does it mean? It means actually the refractive index of the medium is a function of wavelength lambda. It means the refractive index of the medium depends on the wavelength of the wave passing through it. So for different wavelengths of electromagnetic wave, the refractive index of the same medium will be different. In other words, you can also say that this refractive index depends on frequency of the wave. Actually, this variation of refractive index, or you can say this variation of relative permittivity epsilon r of the medium with the wavelength of the wave or frequency of the wave is known as dispersion. This is a very important phenomenon, and we will see actually in detail that this phenomenon dispersion in our forthcoming lecture. Actually, as I have told you, the variation of refractive index or the dielectric constant of a medium in accordance with the wavelength or frequency of the wave passing through it is known as dispersion of the wave. Actually, we know that intensity of electromagnetic wave decreases as it advances into the medium. Why? Why intensity decreases when the wave passes through a medium and it actually advances in the medium? Because in fact, during this propagation, actually two phenomena take place. First one is known as a scattering of the wave, and another is called absorption of the wave. In fact, due to this scattering of the wave and the absorption of the wave, actually the intensity of the wave decreases. So you can say that the reduction in intensity of a beam of electromagnetic wave traversing a medium is partly due to a scattering and partly due to absorption. The phenomenon of scattering and absorption and dispersion, you can say, are in fact inseparably linked, and it will be discussed under the study of interaction of electromagnetic wave with matter on microscopic scale. So this is the subject matter of a study of this interaction on microscopic level. In fact, in this microscopic scale, we actually study this important phenomena, that is dispersion, and along with a scattering of wave, absorption of wave and dispersion of wave. These are the three important phenomena which will be discussed in detail when we will study the interaction of electromagnetic wave with matter on microscopic scale. Remember, this is the subject matter of the microscopic study. In fact, in the previous chapter, let us see, in the previous chapter on propagation of plane electromagnetic wave in different media, the problem was treated as a macroscopic problem, not microscopic but macroscopic, MACRO, macroscopic problem. In fact, in such type of problem, we have treated the relative permittivity epsilon r, the relative permeability mu r, and the conductivity sigma of the medium. We have taken actually constants. But actually, this approach, that is when we take epsilon r, mu r and sigma as constant, in fact in that condition, or you can say this approach cannot account for the variations with frequency which actually take place in case of the dispersive medium, that is the refractive index or epsilon r actually varies in accordance with the frequency of the wave. But this variation of refractive index with frequency cannot be explained on macroscopic scale. In fact, this is the subject matter of microscopic study, that we can actually explain such a variation of the refractive index with frequency and the wavelength. So, we must look to the interaction between electromagnetic radiation and matter on microscopic scale. When you say microscopic scale, as I have told you, that we will actually discuss on the individual electron level, individual atom level, or individual molecule level, individual nuclear level. So this is all about the microscopic study of interaction of electromagnetic wave with matters. Now actually let us start to deal with the interaction of electromagnetic wave with matter on macroscopic scale. For the convenience of study, actually we will divide this chapter in two parts, as I have told earlier to you. The first part will be interaction of electromagnetic wave with matter on macroscopic scale, and the second part will be interaction of electromagnetic wave with matter on microscopic scale. So first of all, we will study this interaction on macroscopic scale. Actually, when we will study this macroscopic scale study, then first of all we have to know some conditions followed by the electromagnetic field vectors, like electric displacement D, like magnetic induction B, magnetic intensity H, and the electric intensity E. Actually, these field vectors follow or obey some conditions when it passes from one medium to another at a boundary, or you can say that it often happens that if one wants to discuss a situation in which the physical properties of matter in the field change abruptly across a surface, such a surface is known as boundary or discontinuity. In fact, it is necessary to know how the electromagnetic field vectors, electric displacement D, magnetic induction B, magnetic intensity H, and the electric field intensity E actually change when one goes across the boundary. In fact, that conditions are actually known as boundary conditions. In fact, in this introductory lecture, I am just mentioning the boundary conditions followed or obeyed by these field vectors without any proof. But in next lecture, just after this lecture, we will actually prove all those boundary conditions. So for your convenience, I have just mentioned or written all the important facts of this lecture, and so we will only know just an information regarding these boundary conditions. First of all, we are going to know what is the boundary condition obeyed by the electric displacement D. In fact, first of all, let us see in this figure. In fact, this horizontal line, this is just not a line, but this is a plane surface, you can say. But in figure, I have shown it just as a line. In fact, this horizontal plane or this horizontal surface, you can say, separates two different media. The first media, here I have denoted it by the number 1, and its permittivity is epsilon 1. Its permeability will be in fact mu 1, you can say. And the second medium above this plane surface is actually medium 2, whose permittivity I have assumed epsilon 2, permeability I have assumed mu 2, And as I have told you, this is a plane surface, but this is not a necessary condition. This surface may be a curved surface. The only condition is that this is just a discontinuity, just a surface which separates the two uh, media. And in this figure I have shown that a beam of electromagnetic wave is incident on this boundary from the first medium, and it passes into the second medium after that boundary. And let us consider that electric displacement in first medium is d1, magnetic induction in first medium is b1, magnetic intensity in first medium is h1, and the electric field vector is e1 in the first medium. And let us suppose these field vectors are d2, b2, h2 and e2 in the second medium. Actually, as I have told you, whenever these field vectors passes from one medium to another at this discontinuity, some conditions are obeyed by them, and those conditions are actually known as boundary conditions. And as I have told you, here in this introductory lecture I am just mentioning the boundary condition without any proof, but in second lecture we will discuss in detail the proof of these boundary conditions, and after that we will actually utilize these boundary conditions in the forthcoming theories. So first of all, what is the boundary condition obeyed by the electric displacement D? In fact, the electric displacement D obey a boundary condition which is stated as the normal component of the electric displacement D is not continuous, but it is discontinuous by an amount equal to the free surface density of charge, and that is mathematically you can write d1n minus d2n equal to sigma. What is the statement? Actually the statement says that the normal component of electric displacement. When you say normal component, what does it mean? Actually, normal component of electric displacement means component of electric displacement at this boundary and directed in a direction normal to the boundary. In fact, I have shown here this line as normal, so we have to take the components of this d1 and d2 along this normal, and these components are actually d1n and d2n. You can see this d1n is normal component of displacement vector d in medium 1, and d2n is normal component of d in medium 2, and sigma is actually free surface charge density. When you say free surface charge density, it means this is surface charge density of free charge. And since d1n minus d2n is not equal to 0, but it is equal to sigma, if in fact d1n minus d2 when d2n will be 0, then you can say that the components along the normal in both media are same, that is they are continuous. But this is not equal to 0, it is in fact equal to sigma. So we say that the normal component of electric displacement is not continuous, but it is discontinuous at the boundary separating the two media, and it is discontinuous by what amount? By amount which is equal to the free surface charge density. So remember this, d1n minus d2n is equal to sigma. This is the boundary condition obeyed by the electric displacement D. In fact, in similar manner, now we will see the boundary condition which is actually obeyed by the magnetic induction B. In fact, this statement, the condition can be stated as the normal component of magnetic induction is continuous across a surface of the discontinuity, that is b1n minus b2n is equal to 0. You can see Actually, the normal component of magnetic induction B at the discontinuity or at the boundary is continuous. So, normal component you can see from here that this B1n is actually equal to B2n. And so, in both media, the normal component of magnetic induction is same, and so it is said that the normal component of magnetic induction is continuous at the boundary. Now we will see what is the boundary condition for the magnetic intensity H. In fact, this condition is the tangential component of the magnetic intensity is not continuous, but it is discontinuous by an amount equal to the free surface current density Js. Remember, here we have to take the tangential component of H. When you say tangential component, what does it mean? This is in fact component of H along the boundary. Normal component means component normal to the boundary, and this is component of the field vector along the boundary. So the tangential component of H is actually not continuous, but it is discontinuous by an amount which is equal to free surface current density Js. So it is mathematically written as H1t minus H2t is equal to Js. Here H1t is what? This is in fact tangential component, that is component of magnetic intensity H along the boundary in first medium, and H2t is the tangential component of H in the second medium. And you can see from here this H1t and H2t are not equal, but their difference is equal to Js. So it is said that these tangential components of magnetic intensity is not continuous, but they are discontinuous by an amount which is equal to free surface current density. Now finally we will see the boundary condition obeyed by the electric field vector E. This condition is the tangential component of electric field vector E is continuous across a surface of discontinuity. Here again we have to take the tangential component. You will see this is a very remarkable condition which will be invariably used in the forthcoming theories. So mathematically you can say E1t minus E2t is equal to 0, and simultaneously we can write it in this way: this E1t is equal to E2t. It means the component of electric field vector in both media along the surface of separation are same, and so it is said that the tangential component of the electric field vector E is continuous at the surface of separation or at the discontinuity. So as I have told you, in this lecture I have just mentioned these boundary conditions without any explanation or without any proof. Actually in the next lecture we will deduce all these boundary conditions obeyed by the field vectors D, B, H and E. So this is all about the introductory facts regarding the interaction of electromagnetic wave with matters both on macroscopic scale and microscopic scale.